So we are looking at polynomial operations lesson number 3, multiplying two binomials on page 285. So if we're talking about using area diagrams, that's a nice extension from what we did with multiplying a monomial times a polynomial using our area diagram. So now looking at multiplying two binomials. And so again, we're looking at us having a length times a width, and the product is the actual area of the two together. So we can see here we've got our positive x plus 3 multiplied by x plus 2. If we fill in the area model, so we can do it in a couple of ways. I know some of you like drawing those individual tiles. So x times x, that's going to give us our positive x squared, and then our x times 3 gives us 3 positive x's. So these are of course all shaded in because they are all positive times positive, giving us positive. Then we've got 2 times x, so then that is 2x, shade those in, and then in the corner here we've got 2 times 3, which is of course going to be 6 unit tiles. So that tells us then when we combine every like term together, we've got an area that is x squared plus, and we've got 2x's and 3x's or 5x's plus 6 units. So x plus 3 times x plus 2 is x squared plus 5x plus 6. So let's take a look at the second example. So again, we've got our length times our width. It doesn't really matter which order you do it in, same thing. If I was to write here instead x plus 2 times x plus 3, it's still going to give me exactly the same area or product of x squared plus 5x plus 6. So along the one side, you can see we've got 2x plus 1. They're all shaded, so it's all positive. Across the top, we've got x plus 4, again, all positive. So we're looking for the area. This time I'm going to do it by drawing the big outside rectangle. And then everywhere where there is a space, I'm just going to draw a line through. And just being careful to be neat, because that way your x tiles actually look like x tiles, and our unit tiles look like unit tiles, and our x squared tiles look like x squared tiles. So it should look something like that. So we can see here as well, this is an x by an x. So that's our x squared, and then that's another x squared. And these are all positive. That's an x times a 1, so that's a positive x. And then we've got more positive x tiles right here. And then our units, so we had 4 times 1, and so then we've got all of our positive ones at the bottom then. So our product then is again the area of this rectangle, so we can see that it is 2x squared. And how many x's do we have? I've got 8 x's here, another x on the bottom, so plus 9 x's and plus 4 units. So take a moment, hit pause, and complete examples C and D. These ones, the difference, of course, is that they include some negatives. So consider how negative times a positive, what happens there, negative times negative, etc. So write in the factors as well as the product, and draw in that area to help you figure out what that product is. So taking a look at C, we can see along the one side we've got x and negative 2. Across the top we've got x and negative 3, or x minus 3. And when we draw in that area diagram, positive times positive is positive. Positive x times negative 2 here, it gives us negative 2x. Positive x times negative 3 gives us our negative 3x, and then negative 2 times negative 3 gives us our positive 6. So our area is x squared minus 5x plus 6, and that's our product as well, of course. So taking a look at D, similarly, we've got x plus 2 along the side, across the top, 2x minus 1. And when we multiply those out, draw in our area product, we have then 2x squared, and you can see we've got positive 4x and then a negative x. So as we've talked about before, a positive and a negative can cancel each other out. So that means that I've got positive 3x and then minus 2. Or if you wanted to, you could actually also write in exactly what we have first. Whoops. And we had 2x squared plus 4x minus x minus 2, and then clean it up after the fact. So 2x squared plus 3x minus 2 is our product. Okay, let's take a look. So just to simplify a little bit, rather than drawing out all of those tiles, we can also just do what some people call a box method. And so we've got x plus 2 across the side here, and then x plus 3 across the side, and then it almost becomes like a battleship sort of thing. Or if you take a look at it as this is the length x and the width x, and therefore we've got an area of x squared, x, and positive 2, an area of 2x, 3 and x is 3x, and 3 and 2 gives us 6, and so we combine that all together to give us x squared plus 5x plus 6. So if we take a look at trying a box diagram for something like this, this helps us where we might be limited with algebra tiles. So we could show 5x minus 6 times 2x plus 1. However, it's going to be a larger diagram with tiles because of the 5x's and the negative 6. So it's a little bit faster, perhaps. We'll test later on that. So across the side, I've got 5x and negative 6. Across the top, I've got 2x and plus 1. So let's take a look at these. I'm going to just switch a color so that you can see this. So 5x and times 2x, that gives me 10x squared. 2x times negative 6 is negative 12x. 5x times positive 1 is 5x. And then 1 times negative 6 is negative 6. So our area then is 10x squared plus 5x minus 12x minus 6, cleaning up our like terms, 10x squared minus 7x minus 6. So let's try B together. So again, on the outside, along the one side, I've got a squared and negative 5. Across the top, a squared and negative 8. So this would be an instance as well where algebra tiles wouldn't work because we can't have degree 2 as one of our side lengths. So this is where a box method type thing would work out well for us. So a squared times a squared, using our exponent laws, we know that that's a to the 4th. Negative 5 times a squared is negative 5a squared. Negative 8 times a squared is negative 8a squared, and then negative 8 times negative 5 is positive 40. So again, we could just write everything out. A to the 4th minus 8a squared minus 5a squared plus 40, and then combine our like terms. So a to the 4th minus 13a squared plus 40 is then our product. Okay, so that similar thing actually totally works if we are doing long multiplication. So you can take 32 times 34, for example, and make an area diagram out of it by splitting it up into 30 plus 4. So obviously that's our 34. And then 30 plus 2 is obviously our 32. And that would be kind of a neat way to go through and end up with the same product. And that's essentially what you're doing when you're doing long multiplication anyways. And I know I've seen some people who are actually taught doing long multiplication using an area diagram or a box method, so to speak. So Let's continue on though. So multiplying two binomials using the distributive property. So I'm just going to skip the little blurb first and come back to it in a moment because I want you to take a look. If we've got x plus 3 times x plus 2, so earlier we had done it as using algebra tiles, or we looked at how we could do it using a box method. So you can see I've kind of outlined the boxes for examples A, B, and D. So if you wouldn't mind just doing that in your books and filling those in to write out the product, and then just hit pause and we'll come back to it when you're ready. Okay, so if you've filled in those boxes, then we can see that we've got, without simplifying, we can say that our area is, let's write it over here, x squared plus 2x plus 3x plus 6. And here we would have for B, 2a squared minus a minus 14a plus 7, and here we've got x squared minus 5xy plus 4xy minus 20y squared. And so what I want you to consider is take a moment and say, okay, well, I don't want to be having to draw boxes forever. Certainly lots of you want to avoid algebra tiles. So how can we look at x plus 3, x plus times x plus 2, and end up with a product x squared plus 2x plus 3x plus 6? Or looking at that, if you think you have an idea of where that product comes from, see if you can extend it to part B and example D as well. And so there's two ways to go about looking at that. So one way is what they've talked about above, which is the distributive property. So what they're doing is they're essentially taking that x plus 3 and x plus 2, and I think of it as distributive property, or even a handshake problem, is so we've got our, we've got our x, and that's going to multiply by the x and by the 2. And so you can see here, just like they've shown here, a times the c and times the d. And then we're going to take that second term, b, and multiply it by the c and by the d, or 3 times the x and 3 times the 2. So we can think of it as distributive property. So we can say that this is x times x plus 2, or x squared plus 2x, and then 3 times x plus 2, or 3x plus 6, and then of course when we combine our like terms, x squared plus 5x plus 6. The other way to look at it is, rather than thinking about it as distributive property, other people have come up with kind of an acronym that you frequently hear called FOIL. And so FOIL is what they've got underneath here. So that is where we're using the distributive property for multiplying a binomial times a binomial. And that's the limitation on FOIL, is it only works when we're looking at binomial times binomial. The thing is if you're doing the box method or you're doing distributive property, it will always work, regardless if it's a monomial times a binomial, a trinomial times a trinomial, a binomial times a trinomial, any polynomial times polynomial. Distributive property will always work. A box method will also work, or another way to think of it is almost like a little meet and greet. So if you've got person A and person B that are hanging out and they're walking through the mall and they bump into person C with person D. So A says hi to C, A says hi to D, then B says hi to C, and B says hi to D. And so it's like a little handshake problem, we call it. And so it's the same thing that's happening here. So x times x, x times 2, 3 times x, 3 times 2. a times 2a, a times negative 1, negative 7 times 2a, negative 7 times negative 1. And so you can see that that is the order of the products that we have it. So FOIL, that stands for first. So we're multiplying the first term in each bracket. So that would be P times 2. Then the outside 2, so P times negative 8 or negative 8P. Then I in FOIL, so that's the inside 2, so negative 8Q. And then the last in each bracket, which is negative 8 times negative 8, or positive 64. And in this particular case, we cannot combine any like terms. There are none to combine. Okay, let's just backtrack for a second. For B, I did not combine my like terms yet, so it's 2a squared minus 15a plus 7. And for D, combining those like terms, we've got x squared minus xy minus 20y squared. Okay, so let's take a look at class example number 5. So I'm looking at FOIL to determine each product. So FOIL first, so we're looking at first is x times x, which is x squared. The outside 2, so x times positive 4, so plus 4x. I inside is 6, positive 6 times x, or plus 6x, and L for last, positive 6 times positive 4 is positive 24. So combining like terms, x squared plus 10x plus 24. I'm going to skip down to B. So the key thing with B is remember squared. We've talked about exponents before. What is the base for this exponent 2? Everything inside brackets. So that essentially means 6a minus 5b times 6a minus 5b. And I would strongly suggest that you write that out before you go into either that box method, distributive property, or FOIL. So again, hit pause right now and come back and see if we get the same thing. Okay, so looking at FOIL then, we've got first 6a times 6a, 36a squared. Outside 6a times negative 5b is negative 30ab. I inside negative 5b times 6a is negative 30ab again, and then negative 5b times negative 5b for our last terms is positive 25b squared. Combining our like terms, 36a squared minus 6ab plus 25b squared. Okay, so please let me know if you have any questions and complete the assigned questions for homework.